Alright, silly people, here's the situation. We are dealing with a harmonic oscillator, and we're going to be looking for the um, expectation value of position, the expectation value of position squared, um, with the expectation value of momentum and the expectation value of momentum squared, and the expectation value of kinetic energy using the substitutions for the position and momentum operators given as superpositions of the raising and lowering operators for the harmonic oscillator. Um, so getting right into it, x is going to be given by an integral over all space psi n star x psi n dx. We'll go ahead and apply that substitution, pulling out the root h bar over 2m omega out of the integral, and then inside you'll have psi n star a plus a minus psi n dx. So we're going to have to find out, well, I guess we don't really have to find out, we just have to use the fact that the ladder operator times state n, ladder up will give you square root of n plus 1 times state n plus 1, and then the lowering operator will give you root n times the state root n, just n minus 1. So applying that to our calculation of the expectation value of position, you'll have psi n star square root of n plus 1 plus root n, root n plus 1 times psi n plus 1 plus root n psi n minus 1 dx. And then we can also use the orthogonality condition that if you're integrating over all space a psi n psi m, or psi n star psi m in the simple harmonic oscillator, that is going to be equal to a Kronecker delta nm. So if n and m aren't equal, this will go to 0. So this whole integral is 0. Bam, bam. Equals 0. For x squared, it's much the same thing. We're going to be pulling out the squared normalization term, psi n star a plus a minus squared psi n dx. So we do have to expand that square, and it's going to be a plus squared plus a minus a plus a minus squared times psi n. Useful to go ahead and just calculate what all these are. So a plus psi n is given by root n plus 1 times a plus psi n plus 1, which is going to be the square root of n plus 1 times n plus 2 psi n plus 2. A plus a minus psi n is going to be the square root of n times a plus on psi n minus 1, which is going to be the square root of n times n again, so n squared, times psi n, so it's n psi n, and then a minus a plus on psi n is given by root n plus 1 times a minus on psi n plus 1, which will give you n plus 1 squared psi n, which simplifies to just n plus 1 times psi n. Finally, a minus squared on psi n is root n on a minus on psi n minus 1, which is going to be n times n minus 1 times psi n minus 2. We can plug all of that into our expectation value. Or we could not, and we can just recognize that in the integral, anything that has a psi n plus 2 or n minus 2 left over will evaluate to 0, and just keep the other stuff. So keeping the normalization factor, it'll be the integral of psi n star times psi n, and we had an n plus 1 term, and we had an n term. So we can pull out that 2n plus 1, and then the remaining integral evaluates to 1. We can factor that 1/2 through to get h bar over m omega times n plus 1/2. That's your expectation value for x squared. For p, the substitution was this stuff, so I'm going to pull that down. So for p, it's psi n star p psi n dx, which is I times the square root of h bar m omega over 2 integral psi n star a plus minus a minus psi n dx. We already know that a plus and a minus evaluating on psi n is going to change the state to either plus or minus 1, so this integral is also just going to go away, and you'll end up with 0. So for p squared, though, we'll have squaring the radical, we have I squared h bar m omega over 2 times the integral psi n star a plus minus a minus squared dx, or actually times psi n dx. The I squared turns into a minus sign, and I'll expand the square for a plus squared plus, or actually it's minus a plus a minus, also minus a plus a minus squared psi n dx. We know that the stuff attached to this operator and this operator will go away, and we know the results of the other operators already, so I'm going to plug those guys in. Minus h bar m omega over 2. It'll be minus, what was it, n plus 1. Or actually, we'll keep the we need the psi n star. It was actually just minus n psi n minus n plus 1 psi n. Factoring out the negative sign and the 2n plus 1 stuff again. You get the integral psi n star psi n dx, which evaluates to 1. You can factor that 2 through to be h bar m omega times n over 2, or actually just n plus 1 half. All right. That's p squared. We can go ahead and look at the uncertainty relationship now. So sigma x is going to be the square root of x squared with x squared. And those are both numbers that we know. And it's going to be square root h bar over m omega times n plus 1 half minus 0. So it's just root h bar over m omega n plus a half. And then sigma p will be that stuff there. We also know the values for both of those. So it's going to be h bar m omega times n plus 1 half minus 0. So it's just square root of h bar m omega n plus 1 half. Multiply those guys together, sigma x, sigma p, and you'll get the m omegas will cancel out, so you just have h times n plus 1 half, which is certainly greater than h bar over 2, or greater than or equal to. I think n can be 0, I'm not sure. So it satisfies the uncertainty principle. We can also calculate the expectation value of kinetic energy, but using Iron-Fest's theorem, it's literally just the expectation value of p squared over 2m. M isn't going to change, so it's going to be 1 over 2m times the expectation value of p squared. So h bar m omega over 2m times n plus 1 half. And then the m's will cancel out, and you can factor an additional 1 half through the thing, I guess. H bar omega times n over 2 plus 1/4. All right.